So now let's look at this idea of a trip point. V out versus V in, and we said that the ideal curve for this inverter should be like this. Right? At maybe VDD by 2, there's a sharp transition. Right? Of course, in reality, that's not the case. We have something like this. Okay. So it's quite reasonable to assume if this region is quite sharp, this transition region is quite sharp, then if I just plot V in equal to V out curve, V out equal to V in, that is, sorry, the point at which it intersects my voltage transfer characteristic, I can define to be my trip point. Ideally, it's if the characteristics were perfect at that point, the inverter should have tripped, right? So the point at which V out is equal to V in is what we define as the trip point of the inverter. So you may think that, well, the inverter trips as soon as you cross VTN, right? But for other reasons, it is better to define it somewhere in between. Okay, I'll tell you why. So this is going to be called VM. This point I'm going to call it as VM. This is my trip point. So now I want to calculate the value of this trip point. Okay. First of all, approximately tell me in which region of operation will the transistor be in? Saturation or velocity saturation. It really depends on whether it's a long channel or short channel. For now, we will assume it's both transistors are short channel and therefore it's in the velocity saturated region. You can also do a derivation for the saturation region, right? So assume N and P are in velocity saturation region. Okay. So what is VGSN at this point? Let me write it out explicitly again. This is V in, VDSN equal to V out, VGSP equals V in minus VD. Please get used to this. We will use this again and again. VDSP is V out minus VDD. So when V in equal to V out equal to VM, this will simply become VM, right? This will be what? VM minus VDD, VM minus VDD, okay? We will make one more assumption just to not complicate our derivation. Lambda N equal to lambda P equal to 0, no channel length modulation. You can put that in, you will just get some random quadratic equation to solve and it will give you no insight into how it actually controls, various things. Okay. So now, what is the current through my NMOS transistor at this point? Yeah, Kn prime Wn. Okay, now at this point I am introducing the widths of the NMOS and PMOS transistor. We have not really worried about it till now. The length of both NMOS and PMOS will be the same, L. Okay, but the width can be quite different. I am going to call it Wn and Wp. Okay, so let me clarify that here explicitly. I have the PMOS transistor, VDD. This is WP and WN. I am not writing L because both of them are minimum channel length, and in the tutorial you would have seen that they use this technology parameter called lambda. Okay, so typically the dimensions of the transistors are written as a function of this lambda. Okay, so W by L will be, maybe for example, L will be 2 lambda always. This is different from the channel length modulation lambda parameter. This is a technology parameter. So if you are in a particular technology, 180 nanometer, that means the channel length is 180 nanometer, 2 lambda is equal to 180 nanometer. So for 180 nanometer technology, lambda is 90 nanometer. For 90 nanometer, lambda is 45 nanometer. Okay, the reason is this scaling sort of worked very well in older technologies. Okay, everything was represented just in terms of this technology length parameter. All design rules, everything that worked well that time, it doesn't work anymore. But for historic reasons, you just need to be aware of this. Okay, so length is 2 lambda. WP is something I don't know. We'll have to fix it. This is WN. Typically, this will be 4 lambda and this will be 8 lambda. Okay, and in 180 nanometer technology, 2 lambda equal to 180 nanometer. Okay, and also let me write lambda not same as channel length modulation, lambda n comma lambda p. Don't confuse it with that. Okay, now let's come back to the equation. IDSN is Kn prime W n by L into Vd sat n, right? What is VGSN? Vm minus Vt n minus Vd sat n by 2. That 1 plus lambda V out I am leaving because lambda n equal to lambda p equal to 0. IDSP is Kp prime what? Wp by L Vd sat p into, sorry, Vm minus Vdd minus Vtp minus Vd sat p by 2. Okay, when V in equal to V out equal to Vm, these are my current equations, assuming both devices are velocity saturated. This, it might surprise you, is a big assumption. Okay, when you actually solve a numerical, and you will see it in the tutorial, you solve this with the assumption, you solve the equations, you get some values. Now you go back and plug these values into these conditions and see, you will find that it may not be true. For example, one of them might be in linear region. Okay, so be aware that unfortunately, unless you give me numerical numbers, I cannot verify this for you, right? So right now that's why I'm saying this is an assumption, it's not cast in stone. Keep this in mind. In the tutorial you will see an example of this. Okay, so now what do? I have to go back to my old condition, IDSN is equal to minus IDSP, right? Therefore IDSN equals minus IDSP. Of course, this is not implies. I go and equate this, right, which implies Kn prime Wn by L into Vd sat n into what? Vm minus Vtn minus Vd sat n by 2 equals minus Kp prime Wp by L into Vd sat P into Vm minus Vdd minus Vtp minus Vd sat P by 2. Clear? So of course all of this goes away. Okay. Now let me define Kp prime Wp into Vd sat P by Kn prime Wn Vd sat n equals R. Okay. Quick sanity check. Is R a positive number or a negative number? Okay. Kp prime is a negative number. Vd sat P is also a negative number. So negative, negative, positive. R is a positive number. Okay. Now can you go ahead and derive the expression for Vm in terms of R and the remaining technology parameters? Of course Vdd is also there. Are you getting this answer? Yeah? Okay, very good. So now let's look at some, let's see how to interpret this, right? I mean, first of all, there are too many terms in this. Okay. So let's make some assumptions that Vd sat n equals minus Vd sat P. Okay. And Kp prime, I have no control over that because that is approximately 2:1, right? Mobility, or 1 by 2. Let's assume that Wp by Wn equals Kn prime by Kp prime, rather by mod, I would say. So what does this condition give us? What is R? 1. Clear? Implies R is equal to 1. Okay. Now apply the same condition out here. Vd sat n equal to minus Vd sat P. Where will Vm land up? Yeah? Vdd by 2, right? Because this is now And of course, I'm also assuming VTN equals minus VTP. Technology is symmetric is what I'm assuming. This implies Vm will simply be VDD by 2. Okay. So if you are, of course, Kn prime by Kp prime is usually approximately 2. Okay, mu n C ox. If you take that ratio, this is approximately 2. So if Wp by Wn is 2, then Vm would land up at VDD by 2 approximately. Okay, but even otherwise, this would be somewhere around that VDD mark. Okay. Now what happens if my Wp goes up? Yeah? Sorry? Vm will decrease. Actually, that's not very obvious from this equation because there is a R on top, there is an R below and all that. So therefore, this may not be so obvious to understand. Okay. So let's see if we can first get this intuitively. Okay, then we'll go back to that. V out versus V in. This is, okay, somewhere here is my VDD by 2. This is V in, V out equal to V in equal to Vm. Okay. Now if I increase my Wp by Wn, I want to know how this curve will shift. It will shift to the right side. Let's see why. Okay. So he is saying the following. Why do you think this should happen? Yeah. So basically the PMOS gets stronger, that is the width of the PMOS is going up. That means the PMOS current is stronger for the same Vin as I would have had for the earlier case, right? So if that is the case, then where should V0 land up? Huh? No, why? That's what I'm asking. So for the same V in, right, you are saying that the PMOS now has a higher current, right? So how will V out adjust itself to accommodate this higher current? So if my width goes up, I'm able to accommodate more current in the PMOS transistor just because of the width. That means my VDS can come down, right? I don't need higher VDS to get the same current. So therefore the VDS has to drop. That means the V out will go closer to VDD, right? And that's what we are seeing here. If you look at it, for the same for the same input, the output is closer to VDD for the case when Wp is higher than Wn. Okay, so this is Wp by Wn is greater than 2. So if the PMOS transistor becomes stronger, then the curve shifts to the right. Okay. Similarly, if the NMOS transistor becomes stronger, you can apply the same argument. Okay, let's maybe do this thing very clearly so that maybe some of you didn't follow my argument here. VDD. Now my Wn has gone up. Okay. Earlier my reference device was WP by WN equal to 2. Okay, this was my reference device. WP WN by is equal to 2. Now WN has gone up. That means the NMOS is a stronger device compared to this. So for the same Vin, what should happen? The NMOS current is going to be higher in this case. Here IDSN is of this guy is greater than IDSN of reference. Now if that happens, then my V out, which is basically the VDS of my NMOS transistor, can drop because the width is giving me more current. I don't need the VDS for me to give me the current there. Therefore the V out can now drop, and that's the basic idea where we say that if you do this, right, for the same input voltage, the output will be now lower when NMOS is actually stronger. Are you all following me here? This is just the intuitive picture, right? You can go back, maybe simulate this and see how it actually goes with R, right? You can simulate this VTC, change your WP by WN and all that stuff and check what happens. Okay, you will see it. I am just giving you the intuitive picture here. Clear? Any questions? Okay, so now I am just going to give you the quick hint for what happens if the devices are long channel in nature, which means there is no velocity saturation. This guy will go into saturation. Okay, so I want to do long channel device. Same thing we are going to do. V in out, V in equal to V out, equal to V out, equal to Vm. IDSN should be equal to minus IDSP, of course, at all times. Okay. What is my long channel saturation current now? IDSN is Kn prime Wn by L into V in, that is Vm. Vm minus Vtn the whole square. Whole square, I have half. IDSP is half Kp prime Wp by L into what? Vm minus Vdd, right? Vtp the whole square. So what is Vm now? What is Vm? Can you derive it? What is the condition? IDSN equal to minus IDSP, right? Implies Kn prime Wn into Vm minus Vtn the whole squared equal to minus Kp prime Wp into Vm minus Vdd minus Vtp whole squared. So now there is a small trick. Of course, I have a square, so that minus sign you should be careful about, but that's not the real issue because minus Kp prime is a positive number, right? So if I define R as root of minus Kp prime by Kn prime Wp by Wn, Kp is prime is a negative number, minus Kp prime is a positive number, therefore R square root, no problem. Clear? When I take square root, how do I decide if it is plus or minus? You get my problem, right? Now this is Vm minus Vtn equals plus or minus R into Vm minus Vdd minus Vtp. Huh? Correct. So therefore, no, but so let's go with his argument first. If Vn minus Vth has to be positive, then if I take plus R into Vm minus Vdd minus Vtp, will that guarantee that this is always positive? So therefore the minus sign has to be taken there, correct? Implies Vm into 1 plus R, right, equals Vtn plus R into Vdd plus Vtp. Vm equals Vtn plus R into Vdd plus Vtp by 1 plus R. Okay. So it's very likely you might think that I am doing this plus minus because Kp prime is a negative number. That is not the case. Kp prime negative is already negated by the IDSN equal to minus IDSP, that's taken care of. When you take square root, there is a plus or minus, that has to be resolved appropriately. Okay.